like ERC. So with that, Paul, over to you.
Thank you very much. Good afternoon, everyone. My name is Paul Chernik, and as mentioned, I'm with ERC. And today I'm going to talk about estimating unconventional gas in place resources and reserves. So in the context of today's talk, I'll first give you a brief introduction to ERC and why we're qualified to talk about this today. We'll go into a very brief definition of unconventional gas from a technical perspective, because it's been covered in detail today. I'm then going to touch on the auditing definitions of play, reserve, and everything in between, because that's of critical importance on this topic. I will then go into what we need to do to understand the reservoir, the unconventional reservoir, from a technical perspective, and then finally some conclusions. So who is ERC? ERC is a reservoir evaluation consulting firm. It was restarted in 2003, but is an established name in the UK industry, having been around since the 1970s. We do everything from reserves and resource evaluations through to commercial advisory, geology and geophysical analysis with our associated company, Equipoise. We do reservoir simulation, expert witness testimonials, A&D services, and reservoir technical advisory services. We work with a variety of respected names. Public ones that I can talk about include Centrica, Entelo, Cairn, and we worked with Norsk Hydro before Statoil bought them. The firm has comprised of three principals. The original two founding members are Simon MacDonald. He's our managing director based out of London, and David Wilson, our chairman, based out of Dubai. David was also an original founding member of ERC in the 1970s, and then I recently joined as BD manager. So the reason I'm giving this talk is I am from Calgary, Alberta, Canada, and Alberta is quite a bit farther down the development cycle than the UK. Pretty much all that's left is what UK people would consider unconventional resources. My career has involved working with heavy oil, H2S, tight oil, oil sands, and of particular relevance today, tight gas. Clients I have worked with in the unconventionals have included Syncrude and Penwest. But of particular importance today is the tight gas players. In Canada is one of the bigger tight gas players in Canada, being involved in everything from CBM to tight gas to shale gas. Duvernay was bought by Shell, and they were also a tight gas, shale gas player. And then little companies like Daylight and Midnight. Now, one of the key points about this slide is that unconventional gas is the playground of everybody from super majors to the small independents. So in North America, there are no limits basically into the size of the people that get involved. What changes is at what stage the company gets involved in the process in terms of infrastructure development and knowledge. So unconventional gas, one way we've been looking at it today is from a permeability perspective. Another way is from a total organic content perspective. This diagram was taken from a Weatherford Laboratories presentation. And basically what it shows is that tight sands have 0% total organic content, whereas coals have 100% organic content, or can have. And then shales fall somewhere in between. Tight gas is a relative term. If you read about it in a textbook, it will say less than 0.1 millidarcies. But as we've seen today, we go all the way down to nanodarcies. So in the context of my talk today, I will be saying that tight gas is something where we drill and we perforate, we don't frack, and we get basically no gas, uneconomic rates, uneconomic volumes. And the permeabilities are in the microdarcy to nanodarcy range. The gas from unconventional gas sources comes from two major places, I guess. The free gas within the gas field porosity is where we get gas production from sandstones. The absorbed gas component from the total organic content is where you get the production from coals. And then you get a combination of the two in shales. Unconventional gas reservoirs need advanced stimulation. And although fracturing has been used for decades, the size and scope of these fractures is a little bit different than the historical wells used in the 80s and 90s. Vertical limited entry fracs are used. Multi-stage horizontal fracs are used. We have large sand volumes, 400 tons per frac in a single stage. You can have up to 20 stages per well. And you have cloud propagations instead of the traditional bi-wing fractures in some formations such as high quartz content shales. But it's critical to understand is that different simulation techniques apply to every different type of unconventional reservoir. There is no magic bullet that you say it worked here, it'll work everywhere. Every reservoir is different, and therefore every reservoir must be analyzed on its own for the best simulation technique. So I'm going to take a moment now, put on my auditing hat, and talk about the difference between a play and a reserve. In the UK, we use the PRMS as our guidelines for reserves and resources reporting. It was developed by the SPE in 2007. And all of us are probably familiar with the general categories of prospective resources, contingent resources, and reserves. But what is less used, but in my opinion is critically important in unconventional gases, is the PRMS has a series of project maturity subclasses. Basically, when you go through any unconventional development, you go through a series of learning steps. You go through a series of steps technically, you go through a series of steps commercially. And it's important to know where in that process a company is. So what the PRMS defines as a play is very early prospective resource analysis. Basically, you have no specific information on the reservoir. It's just an idea, it's a concept. You work your way through to a lead and then to a prospect. In the contingent resource category, you have the development non-viable, development unclarified or on hold, and development pending. And what that basically means is you're going through the learning curve, but you haven't crossed the commerciality threshold. And then when you get to reserves, you cross the commerciality threshold, and you can begin to get bookings on P1, P2, and P3. So what ERC has done is it's tried to come up with a series of guidelines which help describe what you need to know to get to what point in the reserves categorization. So as I said before, in a play we have no defined information. We have an idea, we have a concept. But then if we want to get to the point of contingent resource development unclarified or on hold, ERC believes that we need to have detailed geological information. In unconventional gas reservoirs, this means vertical appraisal wells with studies done on core, logs, and cuttings. Geological interpretation must be complete, and we have to have OGIP calculated. Now, I've been told that there's a slight terminology difference between the Europeans and North Americans. In Canada, OGIP stands for original gas in place. In Europe, it's gas initially in place. They're the same thing. To move to a contingent resource development pending, we have to have proof of a company's understanding of technology. They have to be able to demonstrate that they have chosen a technology and they're able to get demonstrated, significant, and sustained gas flow. An initial rate is not enough. You need to have a little bit of decline history to see how the well performs over time. And you'll notice that both of these are still just in the contingent resource categorization, because quite often companies will go through both of these steps. They'll do their geological analysis, they'll do their initial work on the wells from a fracturing point of view, and they will not reach the commerciality threshold. But in order to step into reserves, you have to cross that line, and you have to show that your wells on an individual level are economic. And then finally, what every company wants to try to do at the end of the day is book non-producing locations, PUDs. Proven undeveloped locations. And in order to do that, you have to understand your interference between wells. You have to understand your production profiles in the long term. You have to understand what well density can be allowed, how far you can step out in terms of your step out locations from producing wells. And this all involves detailed reservoir study after wells are brought on production. So in North America, people will argue about this, but I would say that the majority of the time spent in the last few years has been right here. People have been going into great detail into understanding what the limits are of fracture stimulation. And right now, auditors and companies are arguing about right here, the ability to give PUD locations and step-out locations. But in Europe and elsewhere, we're at about this phase right here. So what I'm going to do today in my talk is focus on the geological analysis and how this will step forward into reserves in the future.
Which phase was that?
Oh, sorry. I'm going to focus on contingent resource development and clarified or on hold. So in terms of understanding the unconventional reservoir, a lot of the talks earlier today have described this in good detail in terms of the characteristics that we look for. But to understand what a conventional reservoir is, or unconventional reservoir is, we have to first understand what a conventional one is. So conventional traps are usually structurally or stratigraphically defined within a contained area. And the primary risks are source, seal, reservoir traps, and commerciality. They can often be delineated using seismic, and seismic is a powerful tool. And other than in extreme environments like the Arctic or ultra-deep water, technology typically isn't that much of a risk. We've been doing these for long enough. We understand how to produce them. We understand once we have a resource, how we go about getting it. Unconventional gas sets are a little bit of a different beast. As described today, they are heterogeneous assets. And that is an absolutely key point in my talk. That means that just like any other reservoir in the world, they change. They are fairly extensive, but they have transitions within them. Sometimes these transitions occur over kilometers, but sometimes they occur over meters. An example of one that occurs over sandstones in the Deep Basin in Alberta. Examples of ones that occur over kilometers would be the Bakken in Saskatchewan. The risks in unconventional reservoirs are reservoir quality, rock properties, hydrocarbon fluid type, technology, and commerciality. You'll notice my list is a little different than the conventional reservoirs. Reservoir variation can often not be resolved with seismic. And I have two key words there, reservoir variation and resolution. We can get indications of transitions, and we can pick out possible large-scale sweet spots. But in terms of where these transitions occur from good to bad reservoir, seismic at this point hasn't been much of a help. Although lots of research is going forward to see if maybe it can be more of a help in the future. And typically, not every part of the reservoir is going to be economically viable using existing technologies. So again, it's all about that heterogeneity. It's about how, as was described earlier, the rock is important, and the rock defines good and bad unconventional plays. What I've shown here is a quick map of the North Parachute pad drilling region done by Encana in Texas. This is 1 mile. Each one of these lines is a horizontal well. So this gives you an example of the density that is eventually reached in these unconventional assets. So as somebody mentioned earlier today, the SMI conference happened a couple weeks ago. And there was one presentation that really caught my eye that showed the heterogeneity and the importance of understanding that. There's a company called Drilling Info, which did statistical analysis. And they came up with the map you see here. Basically, they used a very simple algorithm of pay, thickness, and producing GOR in the Barnett. And they ranked the acreage based on those two indicators. Everything you see here in the red and the orange is uneconomic. That's an amazing statement. If you look at the overall shale, that much of it was uneconomic. The economic portion is just this region right here in the green, grayish, and yellow. For scale, this is 180 miles. So this is not a small region, airily, but in terms of the overall shale, it is a pretty small region. And then you begin to look at why. Based on this Drilling Info ranking, they normalize the production profiles. And you can see that in good acreage, the wells perform along this trend right here. Max IPs, according to Drilling Info, are 2,000, and ultimate recoveries are about 6.5 BCF. Whereas poorly ranked acreage down here, this is the H, max IPs of 800 and recoverables of 1 BCF. So we can see through the statistical significance of the Barnett Shale with the 10,000 wells that there are variations in the reservoir, and these do impact production profiles. So how do we define the geology? Now, CBM, tight sands, and shales are all very different kinds of rocks, but they're all unconventional gas assets, and the process by which you go through to define your geology for all of them is similar. The first thing you have to do is you have to understand your aerial extent of the formation in play. Seismic is a very powerful tool for this. You can go through and you get a sense of where your shales are. You can get a sense of how thick they are. And that can give you a good comfort feel that you might have a prospect. Then you have to understand your regional positional environment. This is what the last talk was talking about. Thermal maturity, understanding how rocks were deposited, understanding are you going to be in the Euxinic Basin, are you going to be on the shelf. All of that kind of understanding of your geological environment can help you understand why a place should be good and why you should drill there. But then you have to get down to the nitty-gritty. You have to drill some vertical appraisal wells. You have to take core, you have to take cuttings, you have to take logs. And you have to drill enough wells to have triangulation. I'll go on this topic in the next slide in a little more detail. But triangulation allows you to identify reservoir transitions. And finally, you have to take pressures, because pressures are a critical issue. You have to complete your core and cutting studies to determine your mineralogy, your geochemical and your petrophysical and your geomechanical properties, and your rock fluid compatibility. There is enough understanding and learnings from the US and Canada and elsewhere to begin to find indicators that maybe your shale isn't good, or maybe your tight sand isn't good, or maybe it's excellent. And by doing these studies, you can begin to do analogy comparisons. They also are important for helping you design your fracture program. And then finally, what you do is you correlate your logs to your core, and you use all of your available study work, your seismic, your geological interpretation, to come up with a full geological model. It's a lengthy process, but it has to be gone through. Now, what I've got here is an example of triangulation. This is a very common technique for evaluating and defining reservoirs in North America, and I thought it was worthwhile going over for a moment. So here we have an unconventional reservoir. And I've just simplified this, obviously, but the green is excellent reservoir. This is the dream of every person when they drill. This is what you want to get. Yellow is good reservoir, blue is poor, and red is awful. And we don't know what we have yet because we haven't drilled. But we've used our seismic, we've tried to identify a sweet spot, and we drill a well. So what does this tell us about our unconventional reservoir? It says, at this point, right here, we have good reservoir. That's it. We cannot say anything else about the reservoir because our drilling only tells us about the localized area. Seismic cannot help us find the variations in the reservoir to the definition that we need. So we drill a second well. We get good reservoir, not the same. So we're okay with this, but what do we know? We know a transition occurs between these two drilling points. We don't know where that transition occurs. Does it occur right next to this well? Does it occur right here? We have no idea. And we drill a third well. And the third well hits awful reservoir. So all we can tell is that between these 3 points we have reservoir transitions. Now flipping this around, if we drilled our first well and it was an awful reservoir, does that mean we have to abandon the play? No. It means that we knew at that point we had awful reservoir. So it's one of the things that's different about these kind of plays is that a single well does not define your play as good or bad. It's just a control point. So we need to drill more wells. If we drill 2 wells in these points right here, and we draw a triangle between them, what we note is that the reservoir properties of all these 3 wells are the same. If we know that their distance is close enough together that it makes sense geologically, that we would not have transitions between them, then we can say we've defined the reservoir in that small triangle. And that's all we've defined at this point. And this is how reservoir definition occurs in North America with these fields. as you drill more wells, as you define your reservoir, you keep stepping out. And that becomes important when you get to infill locations, when you get to step out locations. It's about really understanding what you have on your acreage. So the final geological model will combine your seismic, your sedimentology, your core correlated well log information, and your rock properties. And when you study all these and you have identified the discrepancies and the differences, and you reconcile those, you begin to get an understanding of what you really have. And once you've done all of this, you can then risk your unconventional play at a contingent resource development unclarified level. Now, why do we do all this preliminary work? It seems like a lot of work, and I admit that it is. But as I said before, we have the benefit of analogies now. When people in the Barnett or people in the Antrim were looking at shales, when they were looking at them, they had no analogies. They had nothing to go off of. So we have that knowledge resource base. And it's important because what we've learned from that is that unconventional resources, some work and some don't. Examples of successes are portions of the Barnett, the Haynesville and the Montney. I mean, we can argue the commerciality based on current gas prices, but they've been able to get sustained gas flows and they've been able to get decent rates. Much of the Cutbank Catamount in Canada has been a very successful tight gas play, as has much of the Horseshoe Canyon CBM. But there have also been failures. From what I understand, this is from personal experience, but I've been told that much of the Floyd, Conestoga, and Chattanooga shales in the States are not suitable. From my own personal experience, portions of the Deep Basin Wild River region, the tight sandstone, were uneconomic and will never be economic. And portions of the Manville CBM will also not be economic. So if we understand the geology, we can determine what from the analogies carries over. Because not everything will carry over, but some things will. And then we can understand the unique risks of our play. And then we can begin to properly risk the acreage under investigation. So one of the questions that I'm often asked is, how do you calculate the original gas in place? And hopefully what you've gotten from the presentation thus far is that it requires studies. In the case of shales or in the case of coals, you cannot accurately determine, and accurately I mean within the context of reserves and resources, you cannot accurately determine them without some lab work. And that's because you have the adsorbed gas component. You can approximate it beforehand, but to actually get the real number, you have to take it to the lab. And once you've got some core work done, you can correlate your logs to your core, and you can begin to develop OGIP per unit area maps. And what OGIP per unit area maps do is they take into account your reservoir thickness and your storage mechanisms and give you a sense of how the OGIP changes across your working interest land. In the case of sandstones, core studies aren't required, traditional petrophysics work, but what I found in my own experience in Canada is that when you start getting to the extreme infill drilling and the high well densities, the decisions as to whether you're getting a good recovery factor or not are quite important. And companies found who didn't do core that they needed to have that level of precision. So I would recommend core be taken in all situations. What else do we need to think about? Well, it's been discussed previously, but thermal maturity is a very key factor. Knowing whether you're in the gas window, the condensate, or the oil window is critical. The gas window is obviously great. The oil window, there's been a fair amount of discussion in the media recently with EOG and elsewhere that oil shales could be a commercially viable source. But condensate is a very tricky one. Quite often these fields are retrograde condensate. So if you know how difficult retrograde condensates are with conventional reservoirs, imagine them in unconventional. And on top of that, the liquid loading issue from the condensates is a problem for production. So once you've gone through the flush production and you're into the tail, the volume of liquids that drop out from production can be enough to kill the well. So it's something to take into consideration. When you're doing the geological analysis, you have to keep in mind what the next stage is going to be, and that's fracture stimulation. So you need to keep in mind clay, quartz, and carbonate content. the presence of mobile water above and below your formation. You have to be aware of natural fractures and whether these are going to affect your frac job in positive or negative ways. You have to look for natural frac barriers. And you have to think about water supply and disposal. In the Horn River Shale, which is a new play in British Columbia in Canada, they're going to be using the DeBolt saline aquifer formation as water supply and disposal. That's how they've gotten around the freshwater issue. This will be something that has to be investigated in every play that is explored. So in conclusion, unconventional reservoirs can be important and beneficial parts of a company's portfolio. The process from play to reserves is intensive. First, you have to do technical studies and calculations based on drilled well control. You have to have proof of your ability as a company to apply technology to achieve sustained gas flows. Earlier today, it's been discussed that the technologies are cookie cutter, but it's been my own experience that they're not. Companies are quite secretive as to the subtleties that allow for commercial production. You can see it in public literature that every company's production profile trends for their wells are quite different. In Canada, from the drilling info presentation I talked about earlier, there was another slide I don't have here where they showed how in Canada's wells in the Barnett Shale are quite low recovery of gas. EOGs are extremely high, but we don't know what the costs are behind those two wells. So there's a trade-off between cost and recovery. In addition, sometimes companies struggle to get fracture propagation. They could have the frac pressures wrong in a region. And you have to go through that struggle to figure out what the technology is that you need to apply in your reservoir. And you have to do it before you go bankrupt. There were a couple companies I worked with in Canada that didn't figure it out, ran out of cash, and ended up being bought out. So it's something you have to be aware of. And when you're using that technology, initial production rates are very important, but just as important, or even more so, is the long-term decline profiles. It's great if you can get 11 million a day or 20 million a day, but if it declines at 95% and goes down to nothing within 3 months, you probably haven't got a commercial play. And that leads to my next point, which is the demonstration of commerciality. That will be the final threshold that must be crossed for reserves. It's a lengthy process with many steps, milestones, and contingencies. That's to be expected. It's not easy. Companies should use the project maturity subcategories in the PRMS to describe where they are in the process. And investors should be looking for those subcategories to be used to help them understand where a company is at. And yes, that's my presentation. Any questions?
I mean, we heard sort of 2 or 3 different things about the US. The average sort of cost of production and current prices. And, you know, my experience with ERC is that you're actually a fairly hard-nosed bunch of people when it comes to allowing people to book reserves and so on. You know, and I mean, every year Tullow goes through a real powerful meeting with you guys to make sure that everything we do is bookable and that all our fields pass the threshold test, particularly when prices decline. Yeah. I mean, doesn't this suggest that there are some things out there that have been taken as reserves by companies that should not be? Or are you so onto that that's not true?
Well, I think if you look at the reserve write-downs that have happened in the US and in Canada on the unconventional reserve plays, you can see that people didn't get it right initially. I can't comment on US shale bookings, but I can comment on my own experience from Canada. And when people originally looked at the tight gas wells in Canada, the Micro Darcy, to tens of microdarcy range. They didn't appreciate how difficult gas recovery would be and how many wells would be required. So what they had a tendency to do was undercapitalize the reserve reports. And as a result, there has been a lot of write-downs in North America over the last 10 years as people have done that. The pricing assumption is something that's, depending on the jurisdiction you're in, is set by the government or by yourself. But typically, auditors need to be aware of the limitations of the play that they're in, which is why I think a greater emphasis is being placed now on the geological understanding than was beforehand. I mean, if you talk to guys from 10 years ago, they all thought that shales were going to be continuous, that sandstones were going to be continuous. But there's so much heterogeneity now that I think people have, quote unquote, learned their lesson. And we're doing a better job as an industry of risking what's out there. Now, having said that, bookings that were already given, companies are loath to give up. So you'll probably see continued write-downs with some companies. On the other hand, with other companies, you could see reserve write-ups. It just depends on where they are in their booking process.
And to kind of follow up on that and just reflect on what we heard about Europe, I mean, you know, the potential per square mile that Stuart talked about, Europe and North Africa is quite low. It implies you need more wells, more geology, more thinking to sort of characterize it. There aren't enough rigs to test one basin properly, never mind all of them. It sort of suggests that there should be no company that's exploring, if I could use that word, in Europe and North Africa for unconventional resources that should have a single reserve number on its books anywhere. These are all pre...
Most of the things right now are what I would consider the prospective resource level.
Yeah.
And one of the things that's a little bit different about Europe, I'm finding, compared to North America, or at least for Canada, is quite often companies just say a contingent resource. They don't say what the contingencies are. And there's a tremendous difference between it's contingent on drilling up more wells and proving up my acreage versus contingent on getting government approval to downspace. You know, they're night and day. One of them is basically money in the bank. The other one is still high risk. And so I think it's very important for people to ask for and demand that they understand what the contingencies are behind those statements, not just for tight gas, but for all contingent resources in general, so that you can get an appropriate understanding of where you are in the process and the remaining risks involved.
Yeah, good. So if there are any fund managers left in the room, there's a message there. Does anybody have any more questions? Yeah. I'll do the one at the back. Oh, we're headed to the same place, Carl.
Okay. Geological play is only one aspect of unconventional gas. The other is the current day in situ stress, which is going to affect your fracture performance.
Yeah.
I wonder whether there's any way you can weight your reserve estimates according to the very different current day stress fields in different areas.
It's an interesting question. My personal feel is when it comes to resource assignments is that you can theorize how a well will perform based on geological factors like stress environments and such. But a tremendous amount is the proof in the pudding. Some companies, when it comes to these tight gas fields, they struggle to place their sand. They struggle to pick compatible fluids. They make the choice of using gels versus slick waters. So even though you can rank things on a best practice point of view, will a company use best practice? And I think that's important. Hopefully that answers your question.
Well, sort of. I mean, to my knowledge, there's been perhaps 100 geomechanical studies done on tight gas, and probably about 50 on the Barnett Shale. But these have been mostly for wellbore stability, and very few have been addressing fracture permeability and fracture performance. But the very fact that they're needed for wellbore stability implies that they have a very poor understanding of the current day stress field.
Oh, I would say most definitely. I mean, it's only been recently you started to hear about fracture propagation in some of these wells. And I mean, that's quite a unique statement to say I'm going from having bi-wing fractures going out to having these bursts of explosions. People really don't understand exactly what's happening down and why. It's more of a trial and error process.
Black art.
We had two more. So one more at the back. And this one.
This one, yeah. I was very curious. You're putting together the Barnett Shale and some of the Canadian reserves in the same breath. I was very interested, from your point of view as a consultant, how many common denominators there are between the two, because they're very different geologically, aren't they? And,
yeah.
And how that's applicable to some of the European plays.
Well, I've been going to, I had the good fortune of doing some core lab courses recently, and looking at their thoughts on the different shales in the U.S., and then combining it with my own experience in Canada. And if you'd asked me 2 years ago, I would have said that you have to have high quartz content, you have to have very thick, you have to have very brittle, you have to have, TOC wasn't so important, and that's because that's my experience with the shales in Canada. But then I began to look at how these shales in the U.S. perform, and some of them have much higher clay contents, higher TOCs, less quartz and carbonate. Basically, I don't think we've properly defined what is necessary to have a workable shale play. I think people every month are expanding the scope of what they think can work. So as a consultant and as an auditor, I try very hard not to say this isn't possible. I have a tendency to say, you show me it's possible, because we don't know what the technological limitations are yet.
Well, I think a few small oil and gas companies. How long have you been here?
I've been in Canada,
in here.
Oh,
in the UK.
For a year. So
I think there's a few small oil and gas companies around the UK and Europe are going to start having a hard time fairly soon. My sense. But with that, let's stop for lunch. We're already running a little bit late. Just one thing, we need to do the draw.